Okay, so we're going to do now the next problem, which is the case where shocks form, and it's an accelerating piston problem. It's actually not too much more difficult than the dam problem. In fact, maybe it's no more difficult, and it's certainly once you understand the dam brake problem, you'll find this easier to understand. I think it's not as big a step because it contains lots of the same idea. So what we do is we have, here's X and here's H. We have still water, and we take a piston here, and we accelerate, we push this fluid forward. And we have the velocity is given by acceleration times time. So it's constant acceleration. Okay, so the position is given by a half AT squared. That's the position of the moving through the fluid. So we look at the characteristics now. We have all these minus ones coming like that, filling the space. So here are the C minuses. And they all come from still water. So on C minus, we've got U minus 2C is equal to 2 minus 2C naught. So that's true everywhere. And of course, then we've got to work out what's going on with the plus characteristics. So those are the ones that are sloping this way. Now, I'm going to have a bit of a red colour. This is the position of the piston here, a half AT squared. So I've changed this coordinate to be T now to draw the characteristics. So there's going to be some characteristics that are coming off this piston. Of course, they're going to cross. We're going to get a shock. But let's just come back here and go on C plus. We know U minus U plus 2C is a constant. Now, it might vary from plus to plus, but since this is true everywhere, it tells us that U and C are constant on C plus. So it's a bit weird. You can be on C minus, U could be 7 and C can be whatever, right? They can change as long as they add up, as long as they've satisfied this equation. So if U goes up, C has to go down. Whereas on C plus, these are a constant, and because this is also true, we can solve simultaneously. So U and C are constant on C plus. So that X plus is a straight line. Okay, so we're almost good to go here. So we're going to do this characteristic here. We're going to try and consider the one here that starts at some time T naught. Okay, so we're going to do this, but that characteristic there. So what do we know about it? At this point here, let's have a look at that point here. So let's do this as X plus. All right, at T equals T naught, the characteristic starts. Okay, so this is X plus the piston characteristic. Okay, the characteristic that comes off the piston, that's the one we're interested in. These ones that come out here we're not interested in, because they're going to, and of course one of them is going to come up here and hit the one coming from the piston to form a shock, but we'll come to that in a second. Alright, so at T equals T naught the characteristic starts. Okay, so what happens there? Well, we know that on this, we know the plate, we want to find out what is the, we know that the velocity at T equals T naught, the U is equal to A times T naught. So that must, and that's going to be true on the entire characteristic because these things are constant. And then the C, we find, okay, and we'll call it C plate. We find it from this equation that's true everywhere. So we know that U minus 2C plate is equal to minus 2C naught. So now we can solve this. We know U is AT naught minus 2C plate. Alright, just answer the phone. So what do we got? AT naught minus 2C plate is minus 2C naught. So the C plate, which is basically the wave height at the plate and all the way along this characteristic. Okay. Okay, because remembering that, of course, C is the square root of GH. So the speed or the height of the fluid on the plate, depending which one, you can convert one to the other. We solve this equation here. So what do we get? We get C plate must be equal to C naught plus a half a T naught. So we're all good to go here because we can solve for these characteristics, right? We're going to the equation is dx plus dt is equal to u plus c, which is going to be the velocity, which is a constant, which is a naught t, plus c naught plus a half a t naught. Okay, and then we have the and we know that x of t naught is equal to a half a t naught squared. Okay, we know the starting condition here. Okay, and if I solve that equation, I'm just, this should be t naught, of course, okay, because it's a constant, it doesn't vary along it. So this is just a straight line, so I just get x plus, which depends on t and t naught, where t naught is where it starts on the curve. So it's just a sort of a parameter that tells us where they originate from. See, okay, so I just take that and I multiply it by t, and then I've got a minus c naught t naught, this is minus a constant, minus a t naught squared. Okay, so when t is equal to t naught, I do indeed get a half a t naught squared. Alright, so that's the equation of the characteristics that come off, and then we can ask the question about when does the shock form, when do they first meet? Because if two characteristics meet, which you can see here is going to happen, they're going to come out like that, because the slope's increasing, the C is getting bigger, the U is getting bigger. So okay, so when do these guys meet? Well, basically you've got this characteristic this is x of t comma t naught, and this next one here is the characteristic of t comma t naught plus delta t. So I'm going to make some space here. I don't want to write on here, and I don't want to just rub this out here. We don't need this. Just try and squeeze this in here. I don't know whether this is right or not, but that's what I'm going to do. So characteristics meet when x of t comma t naught equals x of t plus t comma t naught plus delta t, and then we just expand that out and write this as x of t comma t naught plus delta t times dx dt naught of t comma t naught. And of course that for these two to be equal, that has to be equal to 0. So the condition, the shocks, we get a shock, the first shock I should say, alright, which is the only one we're interested in, because of course the solution can't carry on past that when dx dt naught equals 0. Okay, so I'm now going to show you the notes quickly here. So there is our solution, and there's if we take the partial derivative with respect to t naught, I get this answer here. And we get, this is the time where the shock first forms, okay? And the first time the first shock forms was the one that comes off at 0. This is the first time it meets here. You can see the lines characteristics getting steeper and meeting and crossing in this picture. And here's the solution coming forward. So this thing here is fine, there's no shock, and then the shock forms here. So the solution overturns, okay, can carry forward on these characteristics. Alright, and then the solution doesn't twist over like that, the fluid doesn't turn over like that, it starts to froth and form some kind of special bore and things. We'll talk about that in a second. Okay, I've gone on a lot, and I don't want to, this piston moving with constant velocity I won't talk about, I'll just talk you through that, but if you get it moving, it's a simpler case, and you the characteristics, you get a shock forming straight away, and you can get this simple expression here for the characteristic that comes from the piston. Okay, I'm not going to talk about that, it's in the notes there.